I did. I didn't have anything to put on your desk. I don't know. Okay. Whoops. How about the tests? I thought were pretty good, all in all. Please look over any comments that I made on the test, and if you have any questions about the comments or your score, you know, you can see me one-on-one, and we can go over whatever question you might have. Okay, and you get to keep the test. Okay. The homework and the take-home quiz, I will get to those this week and get those back to you later. All right. And let's see. And there's nothing due this week, so there's all kinds of stuff due last week. So the nice thing about the week after the test generally is that it's a little bit of an ebb in the work, perhaps. There'll be a homework due a week from Friday that you'll get the homework probably on Wednesday. All right, so what we're doing now, we're starting a new, I don't know, unit, whatever you want to call it, and we're now going to be talking about functions of more than one variable, so functions of primarily two variables, but occasionally three variables. We're going to then be looking at their derivatives, and then let's see, in this unit we'll be looking at their derivatives. We'll be looking at something called a gradient. We'll be looking at something called a directional derivative, where these functions kind of reach a relative maximum and a relative minimum. And then the last thing in this particular unit has to do with a technique called Lagrange multipliers. All right. And so this unit is strictly this chapter 14. Right, and that's enough. Then what follows then with functions of two variables in the next unit, we'll be doing integration, double and I think triple integrals with functions of two variables and change of variables and all that kind of stuff. So anyway, let's get started with this. And so this is 14.1. And it introduces functions of several variables. Functions of several variables. So basically, this function assigns, let's look at a function of two variables. It assigns to each x, y, that's in its domain, a unique real number, and so this time we don't have just a single number in the domain, we have a pair of numbers. And so basically what we have is x and y here are the independent variables. And then usually we call the third variable the letter z. So often we write z is equal to this function of the two independent variables x and y. Okay. And then z here is it depends on the values of the other two variables, so it's called the dependent variable. All right. So just a few examples here, fxy, and let's say it's the square root of x plus y plus 1 all over x minus 1. So we see that there are two variables here, x and y, and for each value of x and y, we have a unique value for the function. So say you want to evaluate f at 3, 2. The first coordinate place is going to be the x, the second is the y, and it's just what you think it would be. You just plug in the number values for the variable. So square root of 3 plus 2 plus 1, all divided by 3 minus 1. And we get what? The square root of 6 divided by 2, and that's the value of the function at that particular pair of numbers. Okay, something else you might be asked to do with these functions, the two variables, is to find out their domain, all right? In other words, the allowable input values. So let's find the domain. And usually we call the domain capital D. Okay, now we've got a couple issues here with this one. We have a denominator. So we know that, for starters, x minus 1 cannot equal 0, so that means x cannot equal 1. So that's one restriction that we have. And then the second issue we have here is we have a square root radical, and we want to look at real number values for this, so we want to have a positive or non-negative value under the radical. So we also have to have x plus y plus 1 from under the square root. We want that to be bigger than, or it could even be equal to 0, all right? If it were in the denominator, it couldn't equal 0, but it's in the numerator. We can have the square root of 0. That's okay to have. All right, so let's see, what does this tell us? X plus y plus 1 is bigger than equal to 0. Well, that means that x plus y, when we add them together, is bigger than greater than or equal to -1. Or if I also wanted to, that's good enough right there. So if we want to put the domain, we can write it in this notation. Put a pair of brackets here, and so this time it's going to be a set of ordered pairs for x and y. And then we have this vertical line, which means the words such that, okay? And then we put our restrictions here. Okay, first of all, x plus y has to be greater than or equal to -1. And finally, comma, x cannot equal the value of 1. All right. Okay. So that would be an answer for the domain. We have to look at what we can't have, and then we can have everything else in our domain. So are we okay with how I obtained that? Now, you might also then be asked to sketch the domain, all right? So we want to do a little rough graph of this. So basically, let's see here. Now, this is just on the xy plane. We're just talking about a pair of some ordered pairs. And for starters, let's look at this one here. X plus y has to be greater than or equal to -1. Well, let's see. I can just do a bunch of, do a table, or I could also subtract x from both sides. So therefore, y has to be bigger than or equal to -x minus 1. And if you remember from, say, algebra, when you are plotting a inequality, you're going to have half of the plane, right? Not just the line. It's going to be half the plane. So the first thing you plot here is you plot the equality, y equaling -x minus 1. You plot that first of all. And so roughly we're going to get a straight line that looks like this when we plot that. And then we figure out which side of the line that we're on. Okay, well here y has to be bigger than or equal to that, so we're going to be on this side of the line. And because there's an equal sign here, this is going to be a solid line. And then finally, we also have that other condition that x cannot equal the number 1. So to indicate that, let's look at the number 1 here for x. What do you think I might indicate that on the graph, that x can't be that 1 in value? We need more than an open circle, though, because we're talking about the whole plane. So x can't equal 1 is a whole big vertical line, actually, because we're talking about the whole plane. So we put a dotted line? Yeah. Let's put a dotted line to indicate that we're excluding that part. Oops, I don't need to go down there. We're just talking about the upward part of it. So that's one way you can show that we can't have that part of the XY plane. Okay, that's our first example here. Let's look at another one. So let's say we're given z equals the square root of 9 minus x squared minus y squared. Okay, so now I'm using z rather than fxy. And we're asked to find the domain D. And let's also find the range. So two things. All right. So with the domain, we want to look at the allowable xy values that give me a real number value for this. Notice again we have the square root radical. So therefore this entire expression here, 9 minus x squared minus y squared, has to be greater than or it could be equal to 0. Greater than or equal to 0. All right? So if I manipulate this a little bit, add the x squared and y squared, I end up getting x squared plus y squared has to be less than or equal to the number 9. Okay, and if we were wanting to plot this domain, basically we know that x squared plus y squared equaling 9, that's a circle with radius 3. So it would be the circle, but we would also want to, and it would be everything then inside the circle, including the perimeter or circumference around the circle, because we have a less than or equal to. So this whole area here would be our domain of x and y that we can have. All right, now the range, we've got to look at this thing. The range, remember, is all the output values. All right, so what do we have here? We have the square root of 9 minus basically two positive numbers. X squared is always going to be positive, y squared is going to be positive. So look at this. We know that 0 is certainly going to be less than the square root of 9 minus x squared minus y squared. Because we can't, the square root is always a non-negative value. But in here, this thing here, the biggest that this can be in here, because this is subtracting off numbers that the squares add up to maybe 9. The biggest that this can be is when we just have 0 and 0 for x, and we just have a square root of 9, all right? That's the biggest it can be. Let me put an equal sign there also. So our output is really squeezed between 0 and 3. All right? So therefore, our range, and so it can be anything between and including those numbers. So the range here now is a single, it's just a single set of values. It's no longer an ordered pair. We're just talking about a single value that we get when we plug in the x and y's. So it's going to be using interval notation from 0 to 3 with brackets around them. Okay. We kind of see how I got the range that this function has, I guess. All right. Okay. Let's see here. Let's look at graphs here of this. And I also have some things that I'm not drawing, which is good. So graphs, the graphs of these graphs of functions of two variables. Now these things can take on all kinds of strange shapes. But let's just say more specifically here, the graph of f, x, y, this function of two variables, is the set of all points x, y, and z. X and y are our inputs. Z is our output. The set of all points x, y, and z such that z is equal to the function at x and y. And we have to make sure that x and y is in the domain. All right. So let's just look at one drawing here. This is here we have z, we have x, we have y axes. So we may have something that kind of looks like a flying carpet up here as our function, and it can go out forever, you know, who knows. So this is our set of x, y, and f of x, y. We are in space now. We're in x, y, and z, three-dimensional. And the domain is going to be, if we look at the shadow of this flying carpet, if we look at the shadow of it, if the sun were right up there, right on top of it, that would be the domain. So the domain here is going to be on the xy plane, and it's going to be those set of xy's that map up to the surface. So this down here is the domain D in the xy plane. Okay. So let's just look at sketch that one function, sketch the graph of f of xy equal to the square root of 9 minus x squared minus y squared. All right, let's just do a very rough sketch of that. Believe me, the best thing to use to sketch these graphs is a computer, all right? I mean, that's ideally what you want to have rather than, unless you're very, very good at drawing, all right, which I'm not. But here I'm just going to do a very rough sketch. So we're talking about three dimensions here, x, y, and z. All right. Basically, let's just look at a couple of points here. When x is 3 and y is 0, then this is going to be the square root of 9 minus 9. So z is going to also be 0. So say a point right here, x is 3, y is 0, z is 0. But also we could have it where x is 0 and where x is, hold it. Yeah, that's right. That's right. Okay. We could have it where y is equal to 3. Yeah. Right. Wait a minute. Is that? Yeah. Okay. Never mind. We could have this point here where x is equal to 0, y is equal to 3, and then again we have the square root of 9 minus 9, which is 0. So our z value is 0. Or we could also have a point up here on the z-axis where both x and y are 0, but z is equal to 3. Because notice when x and y is 0, then we just have the square root of 9, so that's 3. And basically then what we get here is a half sphere. There are other points that I could put here, and it's going to be curving down like this, curving down like this, then going around like this. This is all going to be curved down, and then we're going to have another part of it behind it. It's a half sphere is what it's going to look like. Okay. Because the z values here are going to be bigger than or equal to 0, so we're not going to go below the xy plane. All right. Now, as I said before, computer programs are really good for this. So we typically use computer programs to plot these. And I like to use Maple, but there's Mathematica, there's Math. Yes?
You can get a free app for that going on through 3D graphics.
Really, a free app on an iPhone will do 3D graphs for you. All right. So no reason not to be able to do a 3D graph unless you have a stupid phone. All right, then I can't do anything except hopefully make a phone call and take a picture. Okay, so typically we use computers, and so I like Maple. That's what I used when I did my dissertation. I'm real familiar with Maple. There's MATLAB. There's Mathematica.
Are we going to have to graph
On computers? No. But you know, now here they have on the campus computers. I think they have Mathematica here, but then the problem with that is there's always a learning curve. But they do have Mathematica does have a really good help section to help you through that. That's the problem with any computer type program. You've got that initial learning curve where you put commas where you shouldn't, and you forget to put some things in. And so then also the iPhone. I don't want to forget that then. We can use an iPhone. Did they? Did you? Mm-hmm. Okay. Now, and I'll show you this in a second, these graphs, these 3D graphs on computers, they typically show what we learned were the two vertical traces. That's where lines where x equals some constant h, y equals some constant k, at equally spaced intervals. All right, so let's look at something here. Okay, so we have this. These are two different functions, and actually, I just got these off. I didn't even map these. I just Googled 3D graphs, and I picked a couple of good ones. So I cheated on this. You can see how very odd these things look. I mean, these actually might even be fairly tame looking compared to some of the other 3D graphs that you can see. But the contours up and down depending on the various x, y's. So that's our Z up here, and here we have our XY plane. So, and notice we've got these contour lines going in both directions. I think you can probably see it better on the one that's up above. And these are for equally spaced values of X and equally spaced values of Y. So they give you an idea. Without those kind of contour lines, it's very hard to see on 2 dimensions how this thing kind of moves, unless you have those contour lines. That really gives you the 3-dimensional feel of it by seeing those. Okay. Okay. Now, there's one way of graphing 3-dimensional curves, which is, shall we say, 2-dimensional friendly. And those are if we use level curves. All right. So this is a way of graphing a 3D function. And you've seen these all the time. You've seen these anytime you've looked at a topographic map. Anytime they do the weather, they show various lines for barometric pressure, those kinds of things. Those are all level curves. So let's just give a definition here of a level curve. Level curves of a function of 2 variables, x and y, are curves of the equation f(x,y) equal to some constant k. And we vary what k is equal to give us different level curves. Okay, so let's just look at a couple of level curves. First of all, here's one. What we have here on the right-hand side are the typical kinds of curves that you would see if you graph this function on the internet. So this is minus xy, e to the minus x squared minus y squared. All right, so it shows you 2 different views of the function there. What we have on to the left are level curves. Now, each of these curves are where this function equals a certain set value. Notice here, like this function in this area and this area and down here, the function really changes a lot in value here and here and here. If we go over and look at the level curves, we see that there are a lot of curves here in those areas where the function changes a lot. Where the function starts to flatten out, notice over here the function looks like it's almost a flat plane. Because what happens is when x and y get bigger, e to the minus x squared minus y squared gets really close to 0, and so this thing flattens out. Notice when it flattens out, our level curves start to get further apart because there isn't that much change in the vertical, vertically with the function. So these all give us the same, each one of these level curves gives us a place where the value of z is equal to the same number. Okay, and I think I've got another one here. Right here, now this one, this is a topographic map, and all these lines here are level curves. In other words, that's at a certain height above sea level, all right? So that is the z dimension. And you can be sure that in these areas right here, look at right here, the level curves are really close together. That's where it's going to be, if you were hiking in this area, that's where you'd be putting in a lot of work, okay, because it would be moving up or down very quickly. In these areas here where the level curves are much further apart, things are much flatter, all right, if there's not much change in the vertical dimension of the graph. So that's the kind of information you can get from a two-dimensional graph. Now this also here, this is just another level curve. Here you see that all of these lines here, this is the z-axis. All of these lines pertain to a certain set value of z. Okay. All right. Basically, one thing I want you to note is this. Level curves basically are just two-dimensional curves. They're as if you kind of smashed down your function in 3 dimensions and you left little curves where the function is the same value. So I'm going to say this. The level curves are what are just horizontal traces of the graph and projected down. That's what I meant by squeezed or flattened down to the XY plane. Horizontal traces like here, let me just overlap this for a second. These lines right here are horizontal traces. Remember, we had 2 vertical traces when x is equal to a number and when y is equal to a number, and we have the 3rd horizontal trace where z is equal to a number. So these are all horizontal traces, but they're all then flattened down onto the xy plane. Okay? All right. There's one thing I want to show up here from the internet. Let me do this first of all. I'm going to copy this. Paste. Okay, copy that. This one? No, not that one. This one. Okay. What we have here, okay, these are level curves right here. At each one of these, on each one of these curves, z is equal to a certain fixed value. Now, what we can see here is, let me click on this box here, and this actually shows the surface in 3 dimensions that the level curves correspond to. And the neat thing about this particular application is then I can actually visually here with this raise up these level curves, because they basically, I can raise them up to show that yes, they fit right in there to various z values of the function. Okay, so that's what level curves look like in 3 dimensions. But what we see is that we just flatten them out to the XY plane in 2 dimensions, and then that gives us the level curves for that particular surface. Okay. All right. Okay. I mentioned this before, but when the level curves are closer together, the function is changing more rapidly. So when the level curves are closer together, the function is changing more rapidly. The function is changing more rapidly. All right, and let's see. Let's look at this one here. Okay, let's look at this one. Okay, with this one, whoops, let me get this thing. All right. Okay, here, the bottom one is the level curve, everything flattened down. The top one is our function. The function here is x squared minus y squared. And so this function, it has the shape of a saddle, really. If I could really twirl this thing around, it looks like a saddle. Right here it's kind of flat, but up here it starts to change a lot. Down here it starts to change a lot. Here it starts to change a lot. So what we see here with the level curves is here they're much closer together. This is where that function is going up or going down a lot. Right here in the center, that's where it's kind of at the center of the saddle and it's not moving around very much. And then finally, this barometric map here, we're probably used to seeing that if we decide to inflict watching the weather on ourselves. But anyway, what this just shows various, these curves here all show areas where the barometric pressure is the same. So when we see places here where, look at this big wide gap, I mean, there's a whole state in between these two lines here, okay? That means the pressure is being very steady and there's not a lot of wind and things are very calm. But when you see, like here in the Great Lakes area here, where there is a big change, the curves are very close together, that means the pressure is changing a lot. So we've got wind coming in to make up for that difference. Things are very turbulent. So the point being is that you see these curves all the time. Okay, so basically that's just the introduction to these functions of two variables, what their graphs can look like, what they're trying to figure out what their domains are. Those are the kinds of things that you'll see in the homework on this. Since I hate vacuums, are we okay with this first section? It's not too rigorous, really. Maybe I'll just get a start on this next section. This next section I don't think is too bad, but it's about limits of these functions. So this is 14.2 now. We're talking about limits of these functions of two variables, and we're also talking about where they are continuous at. Okay. So what we're going to basically be looking at is things like trying to find the limit as x comma y. Remember, our domain here is instead of ordered pairs, not just a single number, and say x comma y approaches a set pair of numbers, say a comma b, and we have our function of two variables equals what, if anything, all right? So that's what we mean by finding the limits. So I think one thing I can get out of the way here is just kind of a informal definition of what we mean by limits. Now with this, if you look at the chapter, they do go through formally the epsilon and delta stuff. which you may remember from Calc 1. I don't know how much they cover that anymore with that. And they do have an example very formally of the epsilon and deltas. Anybody know what I'm talking about with the epsilon and deltas with limits? Okay, all right. Well, I'm going to give you some more informal definition. We say that the limit as xy approaches arrow AB of f of x, y. We say that it equals some number L if the distance between the value of fxy and L can be made smaller and smaller. The distance between the function and the number L can be made smaller and smaller as x comma y, my ordered pair, gets sufficiently close to A comma B. Okay. And the important thing here is no matter how x comma y approaches A comma B. All right. Look at this thing here. This is just a more visual thing here. So here we have the surface right up here, kind of again like a flying carpet up there. Here's the z-axis, here's the x and y. And here's a point A comma B for x and y that's on the xy plane. And we are basically then we're looking at x and y, that ordered pair, as it gets closer and closer to A comma B. So in other words, they've got this little circle around A comma B, and so our x and y is approaching our point A comma B. But what we then up here, we have the actual value of, this is the limit value L. It's just a number. And as we approach here, we get different values up here of our z values for the function. So what we want to say is we can get as close as we want to this limit. So this circle around this limit can be made smaller and smaller as long as we're able to get, if we're able to get x and y closer and closer to A and B. Yeah?
Do you always take a sphere out, like, no matter what the shape is? It's not.
No, it's not. Basically, and actually with that I really misspoke. It's really here a interval. What we're talking about here is, this is our L value. So that's really a value on the z-axis. So basically we're talking about, okay, we're trying to get closer and closer to that value. So we're really looking at an interval here, okay? And actually I just kind of, and that's what they have up here. They have an interval. Down below, a circle is commonly what you see for approaching the A and B down below is a circle. Okay. Now the thing is, this x and y, this can approach A comma B from an infinite number of in an infinite number of ways. Because we're talking about a two-dimensional plane down there. This x and y value can circle it any various ways as it approaches it. So we want to be able to get the same limit value no matter how we approach it. We're going to show Wednesday how we can show whether something is continuous or has a limit. Okay, so we're going to show that on Wednesday. Let me get this other definition out of the way, and then we'll stop for today. And that's the definition of continuity. Now, the intuitive way of thinking about continuity is this, that there aren't any holes in it. Remember, for a function of one variable, you may have heard this, that a function is continuous if I can draw its graph without lifting my pen from the paper. So if I can draw the graph and keep my pencil on the paper, it's continuous. That's for one variable function. Here, for two variables, basically, intuitively, the graph has no holes in it, or break. No holes or breaks. All right. It's an intact surface. The more formal definition of continuity is this. We say that fxy, two variables, is continuous at, again, it's an xy pair, we're going to say at a comma b, if we do the limit as xy approaches ab of our function, and that limit is actually equal to the value of the function at ab. So basically what happens here is that the limit exists, the function value exists, we have an f at ab, and the limit is equal to the function value. Contained in that single statement are all three of those facts. So we actually have a function there at AB, we actually have a limit as we get close to AB, and that the limit is equal to the function value. So what we'll do next time then is start looking at where functions are continuous and trying to find their limits. Okay, all right. See you guys Wednesday.